Thank you very much, Massimo, for this presentation. Thank you also for your, let's say, preparation of this event. I've been looking at your other events and how you are organizing the SOS Master, and it's quite an honor to be here. Of course, this program is very high-end and interesting for researchers us within the field. I consider your student very privileged. So I've prepared some material that may, let's say, that is targeted to master students with some insights and some direction on perhaps also how to direct their question, their research and practice related question. All right, so we have 29 participants. If that's enough, I guess I can also begin with the contribution.
I think it's exactly midday, so yes, we can start, and just keep an eye on those that eventually will ask to join, that we don't miss them. But yes, I think it's time to start.
Absolutely. Yes. So as described by Massimo, I had quite a path in, let's say, sustainable architecture, beginning with the doctorate studies conducted between Polytechnic Milano and University of California, Berkeley. And then I began to engage with American practice, such as William McDonough, Skidmore and Merritt, and also working in the United States at the Lawrence Berkeley National Laboratory, which is the place where software such as Energy Plus and such as Radiance and others are conceived. Following, I moved to, let's say, Europe with a couple of years of work for Autodesk, pursuing the development of tools, simulation tools for sustainable building, and find, let's say, the son of Ecotect. At that time, Ecotect was a software, but we were trying to build a new set of tools with more capabilities than Ecotect had. And in this 10 years, I've been working mainly at the EPFL in Lausanne, ATH Future City Lab in Singapore, Architecture Association in London, and been, let's say, contributing to the debate around sustainable cities, sustainable buildings, and sustainable technologies. The content of this presentation, I'm admitting some people. Okay, okay, wow, there is many now joining. Okay, can you hear me?
Yes, very well.
Okay, great. Yeah, so the content of this lecture are related to the definition of regenerative design. You may have heard of it. It's, let's say, a radical sustainability, or a more, let's say, align with Paris Climate and UN Sustainable Goal concept of sustainability. Then we will discuss about urban climate adaptation, what can be certain strategies beyond the conventional one, and then a debate on carbon positive cities and buildings throughout the design of facade especially, and then some mention of circular design, and also of how the built environment can contribute to human health, and not the least to well-being, if we consider that as an extended definition of human health. If we look at the definition of sustainability, we can see that today is defined as something that, let's say, limit the impact of the built environment on the ecosystem. But if we look at a larger picture throughout this diagram, we can see that sustainable design looks basically to a set of solutions that basically do not touch the ecology, but preserve the system as they are. A question can be, but the environment is already being damaged. Don't we need to perhaps reverse damaging processes? And that is what is called restorative design. But if we want to give a higher amplitude to this definition, what if we consider design as something that can enhance and co-evolve together human and natural system quality? So the lecture is around the concept of regenerative design, which to say in a more general way, it is a shift from doing less harm to the environment to do something for the environment, doing more for the environment. Okay, I will admit more people meanwhile. Okay. And also, if we think about the triple line definition by Mr. Elkington, it basically assume that economical systems are of the same importance of ecological system. So he is talking, and that was assumed and adopted by basically everyone, that economical system and let's say ecosystem has to co-evolve. And this is perhaps today debatable, and a new stand, perhaps as this proposed by the Stockholm Resilience Center, is that we have to put things in hierarchy. And biosphere, for instance, it's a layer of major importance. There is someone speaking in the background. If you can please mute your microphone. Thank you. So this is a key aspect, to put a hierarchy of value at the beginning of each of our projects. Also, if we look at, let's say, our languages, if we look at sustainable definition, it's all about reducing damages, reduce the need for new ecological infrastructure, reduce the impacts, reduce the damages, reduce the contribution to environmental damages. These are all taken from article which sustain, let's say, the Bertrand report, or reduce energy, such as energy, water, and materials, or minimize discomfort in the city, into buildings, or minimize, let's say, factor that may harm the quality of life. We can then shift and think of increasing, for instance, the value of natural system. We can think of not only, let's say, limit the use of energy, but create more energy of a certain kind, as well as we can increase and create health. This is called salutogenesis. So this is the paradigm shift that I'm talking about, expressed, let's say, in a few words. Having established the pillars of this contribution, we begin with talking about city. How city can be enhanced in relation to, let's say, nature and not apart from nature. Here is some recommendation that will pop up into the contribution. And the first is to consider multiple factors. And this should range not from only performance-based approaches, but also to qualitative factor. And the second recommendation that I will explain later is to use, let's say, future climatic scenarios to design. The first example is rooted into a work that we have developed for the city of Malaga of re-establishing or regenerate a neighborhood called La Luz. And the first consideration, as you can see here, from the enhancing of the redness of, let's say, a mean radiant temperature in this block, is that it's very important to think of scenarios that are related to future condition. As the microclimate changing, as the climate change is impacting also the local microclimatic phenomena. And this as a series of circular changes that impact other factors. In particular, we can see that the change in the global and the local microclimate is impacting energy consumption. We know, for instance, that building will be much more cooling load dominated versus heating load dominated. So winter are forecast to be, according to, let's say, the majority of the scenarios, to be milder, whereas summer are going to be hotter. The second set of recommendations is about try to quantify also qualitative factors. For instance, here we have a chart with multiple factors that can be considered when we talk about climate adaptation of the city. And together with more, let's say, standard building performance simulation, and those related to performance of building and of outer space, it's interesting to introduce other, let's say, way to account for instance, biophilia. This can be, for instance, a natural view factor calculated, as you can see down here, from different points into space, and as well as a sky view factor accounted as a purely qualitative metric, as studies are supporting the idea that a vision of the sky is something that brings value to the experience and to the well-being. Second recommendation is to choose the right type of simulation in your work. I'm actually polarizing a bit the presentation on these, as I know that at the SOS program there is a major interest into simulation. So I'll try to show some pieces of advice. This APFL campus in Lausanne, where I could stay for a couple of years. And the work we undertake was to simulate the climate adaptation of the campus to future conditions, and also how the campus evolve within new climatic scenarios, and how carbon neutrality could be achieved. To engage with such a large campus with building of different epoch and with different type of material within this fabric, and also with major impacting factors, such as, for instance, a big microclimatic feature which is given by Genève Lake. We have looked thoroughly into existing set of simulation tools, but none of those was actually able to simulate the multiple factors, including all the energy exchanges, as well as the microclimatic feature of the site. So we have further developed a software called CitySim. CitySim is a fast simulator, open source actually, that allows to predict within a very reasonable time all the thermal and energy exchanges that happen into a site. We can call it as a very simplified energy plus, whereas all the set of equations are interrelated to local exchanges, whereas energy plus concentrate more on the inside the building exchanges. So here, for example, is an information about the temperature recorded for a given certain time in the year. And this is a quite powerful tool because it allows, for instance, to establish a relation between building forms and type of carbon performance of each. And then it's possible to associate a color code that establish what type of building should be retrofitted. Furthermore, it's possible to include different, for instance, retrofit strategies and balance and see what is the carbon impact of each of the building and of the campus as a whole. This is, for instance, a calculation as a whole. And what is interesting in this chart is that we are trying here a scenario of adding insulation, which is what, for instance, the Swiss Minergie system would suggest. And it's interesting how all the addition of insulation, which is today recommended by European norms, are going to fail in in future summer, leading to a difference of 7 kilowatt-hour more in consumption. And this is quite an interesting topic, the one of adding insulation, which I will touch perhaps later when we discuss the carbon neutrality of buildings. But for now, just keep in mind that most of the legislation conveying on adding insulation is probably misleading. Okay. Also, it's very important to when you achieve work and when this is possible, to include, let's say, a set of local measurements. To calibrate the model of this campus, for instance, we use 35-meter towers to get all the wind profiles and the temperature profiles at different heights, as well as with the use of a small black globe thermometer to measure mid-radiant temperature. Different points on campus were measured, as well as surface temperature, which is one of the output of the simulation, were sampled and measured for different part of the campus. This, for instance, is a study under the Rolex building of different key point. Some is as the microphone on, if you can please put on mute. Thank you. As you can see, I'm sorry, something. Okay, I should be able to get back. Yeah, as you can see from the chart on your top right, different tools have quite different prediction according to the type of simulated point. So you can find in ResearchGate, I published perhaps 5 or 6 papers on this topic, some information on what tool of when you can use EnviMet, when you can use Ladybug tools, when you can use CitySim, or when you can use, let's say, other software such as Rayman or others. So it's a paradox, but basically not every tool fits every type of context. And depending on the type of exercise or work that you are undertaking, it's important to choose the right tools. There is quite an accurate work looking in all the equations, and this is publicly available on my ResearchGate. Okay, second topic, it's carbon positive building. The first type of recommendation is to look at local climate and do some work on assessing local climate. To do so, especially in Copenhagen, we set in collaboration with the Technical University of Delft and Munich, let's say a series of survey of certain area in Copenhagen, with a real detecting of environmental factors. Those is an evolution of the climate work developed by TU Munich, and we developed this and transform it into a climate cycling in a way. The idea is to combine here, in order to understand the nature of a local microclimate, measurements together with simulation. Here is just, let's say, an open section of one of the devices that can be used to the extent of capturing local information. But those briefly range from wind speed to, in particular, the radiant environment and air temperature. Also, it's quite important in this type of work of relating physiological value as another information. So a set of measurements are taken on a specific part of the bodies that reveal the adaptation.
Il cavo che non funziona.
Come? Sorry, someone is speaking, but if you can be in mute, please. Okay. Okay. And this system allows to automatically track this value and report real time on a map, and generating a map which allows to begin to establish a relation between the nature of site. We can see here a change into some of the parameters when open space are reached. As well, all these are returned into a point with different layer that can contribute to indexes definition. In this case, is the thermal climate index that is reported, which is, as you may know, perhaps one of the most established way to assess comfort in outdoor. Interesting enough, it's possible then to calibrate simulation models in order to begin to establish a certain correlation between different urban forms and the type of experience that can be recorded. And this is a key information not only for outdoor comfort, but also for the energy modeling of building, and weather files or localized weather files or specific point-based information are the actually very much needed information when you begin a design, much more of the simple weather file that you achieve from a weather station. Most of the case, weather files from a weather station are misleading and will not lead to the best design for your climate. Another interesting factor is about geometry, not geometry of the building or urban morphology, but distance and positioning of building for new development. And this is a hot topic, especially for all of the city, such as Milan or others in Northern Europe location, where a new set of tall buildings are popping up. And if we factor that and all the reflection that big tall building implies and the major modification that they imply into the local climate, if we join to this scenario, the climate change scenario that we can see on the left, it becomes quite relevant to understand how to, for instance, distance or play with the array of building. So just as you would do with 3 cards, in this exercise, we have just taken 3 tall buildings and begin to change their distance, even of very minimal fine-tuning modification. So by, for instance, distancing the building from 12 to 30 meters, which may not sound as much in terms of meters, but let's see how the thermal implication. Also, we try to understand how this different layout will perform into different sites within the city of Tallinn. The first, let's say, step is to use Dragonfly or the urban weather generator to create local, let's say, microclimates. The second step is to have a workflow that from one side allows you understand all the temperatures and all of the thermal exchanges, both related to short wave, long wave, and convection throughout computational fluid dynamic simulation. And what is interesting from this first analysis is that you are going to have, let's say, site percentage or hourly or hours of comfort that can differ a lot from, let's say, building array to building array. So this is quite an important information, but we can see, for instance, that one configuration will perform well in one side, but bad in another site in the city. And we can see also that comfort can range from 30 to, let's say, 50 hours, depending on the type of the design and the type of location. So this is quite a relevant information. Small modification can have a big impact. The second point, it's about how the distance between building and how the microclimate is impacting, for instance, what is happening in terms of comfort within the buildings. And due particularly to the co-reflection that happened in between building, and due also to the shade among building, it's quite interesting to see that depending on the type of site, a different layout may be more performative. These are the 3 sites. And we can see that a small modification of the layout can lead to major modification in terms of energy consumption and comfort. Another aspect is about, as mentioned before, a predefined solution as those suggested by rating system, such as the passive house standards, such as the European regulation that concern the thickness and the type of insulation and the, let's say, the transmission. It's mandatory according to European Union. Let's have a critical look at this type of topic. You may have gone through the book Heating, Cooling and Lighting of Norbert Lechner. He sustained that just by building design, it's possible to achieve a saving up to 70%. This is something elaborated in the 70s, which was not sustained by simulation. And it's something that makes generally mechanical engineer quite skeptical, because they believe that mechanical plants has major power. And so, of course, this is a big debate, and we can also take it to the next step in other circumstances. But throughout this experiment, which is basically a 25 million combination of, let's say, very simple building types, from square to rectangular to more elongated, and throughout the modification of building envelopes from more massive to more insulated, we can see that just by architectural manipulation without any mechanical plants, it's possible to reach energy saving that leads to 80%, which means that plants are not needed or very minimally needed. And this applies both to commercial and residential building. Mechanical plants are an addition, but in most of the case, I would sustain is not needed. Okay, including, of course, natural ventilation among the set of strategies. Here, if we go more into numbers, one of the important things, it's about, for instance, U value and let's say, or thickness of insulation. It's interesting, has the very optimal thickness of insulation according to the distribution of value on a Pareto front. It's very, let's say, prescribed insulation thicknesses, which is much lower than those prescribed by regulation, and prescribe much more use of thermal mass. And in certain cases, especially in South, light and purely insulated building will perform much better than insulated building. This is a logical explanation if you think about. Insulation is nothing else than, let's say, a pullover, a sweater, a wool sweater that you put on and that you cannot take out. In summer, this sweater cannot be taken out. So insulation only performs when you have a mechanically ventilated building with cooling, which is not something which honestly we should aim to. Our building should not use a mechanical system, as it's completely possible to not rely into them. So this is quite misleading, and that's why most of the recently designed buildings are overheated into summer. Okay, I will actually demonstrate this throughout a series of buildings that I personally studied into Northern Air Climate, and these are buildings designed by architects for themselves. We have the house of Alvaralto, the Corsmo, Ralph Erskine, as well as Jacobsen house, and each of these is in one Scandinavian country. And also in the second row, we have buildings designed by according to the recent paradigm of passive house, adaptive house, prefabricated house, and so on and so forth. So we have developed all models of this and create any type of, let's say, simulation. So the idea here is to compare environments such as those of passive house, where you want to have a uniform, for instance, luminosity, when you want to have a uniform thermal environment with an equal distribution of heat within the site, and where you have this idea of a building conceived as an envelope, which acts as the walls of a fridge or the walls of an oven. Therefore, you're able to keep the temperature stable, and you're more or less able to control any type of factor. What if we compare, and I'm just taking one of these example among those show, this building to the Erskine house built in a forest in Sweden. This was a building built with no access to any type of industry, because this was built during the Second World War, when Erskine from England reached Sweden to practice as an architect. But what has happened is that this big conflict started, and he had to build something that relates only to, let's say, local source of energy, that only use reclaim local material, that only use material that are fundable within the range of 3-4 kilometers. So some aspects of bioclimatic design that are interesting. For instance, on the northern side, there is no windows, and wood is stacked, especially in winter, to break all the thermal exchanges, the radiant thermal exchanges with the outside. You can see, for instance, that there is a double door that close a space. There are 2 doors in most of the house of this modernist times. We can see certain feature as thermal mass located in certain way, and I'll show also is connected to the outside in order to keep a certain gradient of heat. You can see here, this is an interesting feature, but there is a part which is more related to solar gain. And there is a design of thermal mass in a continuum between outdoor and indoor, so that there is a continuum exchange between in and out. That is the engine, the natural engine, which is basically fueled by the fire and the sun, but is always keeping the house into comfort. It's particularly interesting, this type of drawing, which we definitely should reestablish, where each of the surface is perfectly oriented according to sun path, where window or top window are sized in order to allow for, let's say, a certain amount of light, but also certain quality of light. So there is a thermal zoning, but also thermal, let's say, a light zoning that create, let's say, multiple visual and thermal stimuli between the place. Here you can catch the double door, the vestibulus, if you want to use a Latin term. But actually, this can be, again, a 2 hours lecture, but I'll be glad to share another situation. But to sum it up, what is interesting is that if you look at the numbers, and not only to the quality, what we have is that in blue, and here we have the operational energy, so the energy for heating, cooling, and loading, and lighting, sorry. What we can see is that newer houses are of similar performance of older house. So this is something to think about. Newer house has much higher insulation, reaching 60-80 centimeters. For instance, the Swedish house, they claim to have won a medal for the thickest insulation in the world. And it's not performing any better of the latest house we have seen. But if you look at, for instance, other type of impact, without going into biophysics factor or light quality, but it's something that really needs more time to debate. But if you look in red at the amount of energy needed for constructing new cases, which are the last 4 on the right, and if you look at the amount of energy necessary to build the older cases, there is no comparison. So the embodied energy in the newer case is much higher, also because all the materials are drawn from a very larger network, where if you can see, for instance, Velux window, you can begin to track basically and trace arrow worldwide in order to catch where all the material come from. So this is something to think, and I believe that pre-Carrier, pre-invention of mechanical system or pre-industrialized architecture have certain values that can be rediscovered in modern construction. So my idea is that perhaps we can rediscover, let's say, this way of relating to the site versus this way of relating to the site. I'll just go on because I just have to stay in a certain time, but I'll be happy to come back to that. So also it's quite interesting to think of building as not only in an introvert way, but also in an extrovert way, building that provides something for the outdoor. So in Copenhagen, I've established a series of facilities where we have begun to track with very simple paper-made facade. What's the impact on the indoor, but also a similar, let's say, measurement tool is located on the outdoor. As you can see, here is the facility in Copenhagen campus with measurement indoor and outdoor at different points. And what is interesting, first of all, is that it's possible to calibrate, for instance, tools, as you can see here into this red chart, to match condition that you record on the outside and the inside. So this is a first assessment. We have the tools to monitor both the indoor and the outdoor. So the question is, how can we begin to make a facade that give a positive thermal contribution to the indoor and to the outdoor? I'm not spending any more time to explain that with the warming up of seating, it's important to have cooler streets. And also in winter, in northern air climate, it's important to have warmer streets. So let's begin to think of the envelope as a climate giver, not only for the indoor, but also for the outdoor. Throughout the set of calibration, which are, let's say, a different scale, we begin to see that, for instance, depending on the type of facade, for instance, here we've taken for the retrofit of the building 4 types of facade, from no shading to steady state shading to dynamic Venetian blinds to adaptive facade of different kinds. And the results are quite interesting. We see there is different temperature achieved on the indoor. Okay, nothing new, we knew that. But what is interesting is that we can change a lot the climate on the street, especially for small canyon on this, and also for large space, all the area that are in the proximity of the facade can be controlled by change the facade type. And this, it's been quantified. For instance, this is a study that compare how much just changing the color of a facade, therefore the property of emissivity and reflectivity, so also the rugosity, let's say, of the last layer of the facade. What is the impact of that? We can see that, for instance, in Abu Dhabi, we can have even a difference of 5 to 6 degrees, for instance, in summer, by changing the type of colors and rugosity of a surface. So you understand that with very little, let's say, cosmetic intervention is possible to have a big impact on the microclimate that you experience on the outdoor. Just to provide a major exemplification, changing the color of the facade, just to simplify and target this type of small variable, will have an impact. This is a study in Catania. On the outside, we can see different color of UTCI on the outside. And as we know, we will have also an impact on the indoor. So what I'm advocating for is always, when you design your envelope from now on, to always model the outdoor and the indoor at the same time. Another set of recommendations is about the use of prototypes, because they offer much more insight of simulation. And when you design your strategy, I suggest you to leave your desk and your computer, which also is not very good for your eyes, and try to engage with model. These are some studies I've worked on. This is about phase change material, and with digital printing, we have formed different layouts and try also to create different mixing of phase change material. And this is quite interesting study, also conducted with Kieran Timberlake. It's a study in Boston, Massachusetts. Here it's interesting to understand how different shapes and how different type of paraffin are leading to different type of, let's say, cycles. So this facade can really be printed with very low cost and can grant indoor temperature of a stable, for instance, entity much better than what would, for instance, an hyper-technological envelope, those you can see in today building. Also, if we think about air exchanges, finding very old notes from a professor from the Danish Technical University from the 52, I found these old sketches and tried to develop a custom calibrate and perfectionate the system of air exchanges for a small prototype that I could create in Copenhagen. where here there is basically a natural exchange of air from the indoor and from the indoor and from the outdoor. Here is the sketch, where basically we can use this metal tube in order to exchange heat. And what is interesting by the measurement is that you can extend the time of passive ventilation and of climate of all of this building, basically the majority of the year. It's a small prototype, but it's quite interesting how by exchanging heat from inside and outside, you can basically create a passive building at basically no cost. And last, another example of this is a work for World Health Organization in a country where there is a problem of malaria and discomfort, inability to use nets. So the first study was conducted actually with very small houses of this kind, trying to understand, for instance, as you know, most of the houses are retrofitted with corrugated roof, whereas most of the houses have thatched roof. So, and also ventilation is not curated. So also I try to open a bit like butterfly roof and integrate perhaps the net, the malaria net here as a building, as an envelope feature. What is interesting, and this has been recorded in several ways, it's the type of results which are, I think, much more valid and user-friendly of those of simulation and more accurate. So what we can see, for instance, is that at night, when these buildings are, let's say, occupied, we can see that temperature, these are the nights, are much lower when roofs are touched or when are developed in bamboo, rather than when they are developed with corrugated roof, which is actually what is proposed today. So we can see on the other way that if the building is, let's say, occupied during the day, it becomes much more interesting to use corrugated roof. So depending on the type of building, you can sort of choose the type of roof, and even in houses that have a day and night house, perhaps you can differentiate the roof. And this has been used as a recommendation now for new villages in Tanzania. Okay, when it comes then to another pillar of this presentation, therefore, let's say the topic of circular design and generation of health, I'll propose some of the work we have established along with the Master of Architecture in Extreme Environment. This is a master, perhaps similar to yours, of 2 years, but operates in extreme condition where there is a decrement of quality, whether in a climate, whether in access to this area, or because a cycle have polluted the environment extremely, or because, let's say, human conditions are quite deteriorated. So this master goes every year in a different location. I will keep this collaboration. I moved to Parma University, but part-time professor in Denmark too. And the idea is to use small hacks or small prototypes in order to solve some of this situation, and also collect a lot of information for future design. As you have seen before for the house I've shown before, it's possible from almost a small example to then generate direction for the second semester, where students are able then to create their own project development. I'll show perhaps a video that introduces the work we have done this winter, where we went to the Atacama Desert in Chile. I hope you can hear the sound.
Compleja para evitar vivir en este desierto es la falta de agua, porque el agua que viene en la vertiente de los ríos está disminuyendo. El problema también es que hay muchas mineras. En esta región tenemos muchos minerales, especialmente y sal, que realmente se está explotando mucho el agua, y el agua es primero para el ser humano.
I got this idea of making something that was challenging the heat in a way and kind of embracing it. Because of environmental changes, deserts will be spreading. People will be forced to live in extreme environments. You would use some of the natural conditions here, like the heat and gravity, which is everywhere, to make a system that produces the water and let it back to you. It's like this reclaiming of your own body water.
All humans are innovators. That can be manifested in whatever practice or discipline they're carrying out, and I think becomes crucially important in the practice of architecture. The course's pedagogy is based on stimulating autonomy, empowerment. So we encourage them to detect challenges, create hypotheses of how you would do that differently or more sustainably, and then challenge them to build it. Then we take off in an airplane, and we're there for a month to test that construct.
When I first heard that we were going to the Atacama Desert in Chile, I was very excited. I had never been to South America, and so the thought of experiencing this amazing landscape and new culture as an architect, I thought was very fascinating. It's been a very enlightening process to be able to interact with architecture that seemed to interest so many people, and that also is taken from nature, taken from that.
So one of the important aspects to remember is that we don't want the students to be engineers or scientists, but to recognize the importance of the scientific method in collaborating with different technical competences. Hence the balance between having one foot within the very performance and scientifically orientated aspects of architecture, and on the other hand, a very artistic consideration of what is it that I want to say in the world, where am I talking from, and why. That is reflected in the course, both in the prototypes that they do, and through that exercise, find a program and a building.
Okay, so the idea is to create prototypes that collect information of different kinds. You can also access this in YouTube under architecture and extreme environments, where you have a gallery with many of them related to different environmental topics. Coming back of some of the perhaps direction that may be usable for you, one idea is that we can look into, for instance, circularity, which are external to the cycle of buildings. Here I show perhaps another video of a specific prototype developed by this student. Okay, so I guess you have gotten the idea of these prototypes, but some of these have even scaled up to some patents. For instance, this one, which is about upcycling coal ash as a structural material. We also patent a way to convert sand from the Gobi Desert into a construction material, as well as to use let's say waste wool or textiles and crystal salt available in the Gobi Desert as air purifier. So you can see that all a set of let's say material from other industry can be brought into the industry. Another aspect explored throughout this let's say devices, it's let's say well-being, health, thermal comfort, and establishing at this not only as a pure performance, as a pure numerical factor. Here is an example that, for instance, we just published on energy and buildings, which is about designing spaces and outdoor spaces that relate much more to the displacement of heat and cold sensor within the body. Heat and cold sensor are located in different areas, and each of which is activated at different temperature. So the idea is, what if we begin to look at climate, not according to standard, let's say, measurements, but we look at climate according to the position of thermal receptor into the body. And this can be an information that we can use to design spaces. This has been further developed in the city of Antofagasta in Chile during the extreme environment mission of this year with Amy, an English student I work with. We begin to study through satellite images how different urban patterns determine different microclimates. And then we come up with the idea that although it's a very hot, humid area, adding mist could create major comfort. And this is not supported, for instance, from, let's say, psychrometric chart, where the more you increase, let's say, humidity ratio, the more you will experience uncomfort. The idea standing here is that we can play with the perception of the human and with the location of the body sensor and simulate just some of them. So we create, let's say, a system such as this, which basically create a mist at different height. Throughout a set of sensors, we begin to measure for each of the points within the space and then the surrounding how temperature is distributed. The system spray water, but mainly retain water throughout this very small, let's say, system. what is quite interesting is from one side, they're recording on site a different point of, for instance, the UTCI, and from the other side, the information that come from surveys. It's very remarkable that the system can obviously reduce the local temperature, but the perception of reduction of temperature, which is much needed in that area, is much higher, because other factors such as thermal perception or allisthesia or thermal delight have to be taken into account when we talk about comfort. This is a branch of studies that I will also show later in the later example. So we have perhaps 5 more minutes, so I'll try to go through a bit faster. But I perhaps want to show a further example of how with a small architecture is possible to create a microclimate. We've seen that before, but also I want to share how it's possible to use completely local-based cycle in order to create a microclimate. This is the Amazon forest, where every day you have 1 hour of rain at a given time. And also is a site where there is major availability of bamboo, obviously, and where there is glue, actually rubber, that can be locally made and developed into surfaces. So this is a completely local-based prototype where only the metal rings come from Copenhagen. And this is a system meant to use the local water in order to create microclimate for the 24-hour cycle. And now you can see how it works. So water is collected into plastic bags. These are hospital bags. When water finishes, the hospital bag begins to drop water, and this begins to happen. But what we have achieved is this ring where water is still collected are at a much lower temperature. So they create a mean radiant temperature, the local mean radiant temperature, which is ensured for a few hours after the water event. And we develop many of these technologies that are very intuitive to be used and that add, let's say, a design component. For instance, this is a small and cheap unit to purify air for one house in China, which is completely passive. Or this is a curtain system which employs seedless trees from the forest in order to create outdoor and indoor microclimate of a certain type. Or also, we touch several topics. For instance, how to create protein within, let's say, the Nordic pole by developing certain algae which are actually conserved into the ices. Or this prototype of lamp is basically completely passive. And also the pure water, but it also stores this energy that is then used during night to achieve light. So you can then browse multiple of these, more of these prototypes on YouTube. Now, to conclude, I would like to show some building example. These are come from my practice. The first is the Auckland Cathedral of Christ in close to San Francisco. And these are only examples that incorporate the values that you have seen before. Particularly, these are examples that are incorporating, let's say, biomimicry, the mimicking of phenomena into nature, biophilia. So these are examples that nourish this non-sad thermal aspect. And by playing with the luminous environment, with the color of a material, with the height of space, it's possible to create thermal condition that can make people that comes to this church in comfort, whereas there is no mechanical system. What is very important, I think, in thermal, lighting, and comfort is not to use static metrics, but create always ever-changing environment. This is here activated by these triangular panels that regulate, let's say, light, ventilation, and also intake of heat. And this is also sustained by thermal models, where it's possible to see throughout finite element methods that certain areas, such as the basement here, is kept in full comfort throughout the year by the mean of thermal mass, but also by the mean of all this very high space. Here is another example. This is in Italy. I developed the, let's say, the sustainability concept for the Lavazza headquarters in Torino in the competition phase when the project was awarded. And the idea is that the building, it's a regenerative building, which adds value to the site. The building doesn't, it's according to the solar envelope principle, so it doesn't create, let's say, shape and doesn't compromise the ability for the surrounding building to achieve heat. So it's very important, for instance, if you are modeling the efficiency of the building, but you do two models, one model for the building and one model for the surrounding. I mean, it doesn't exist to me architecture that is introvertly developed just by modeling the performance of the architecture. Is important to model the energy performance of the whole surrounding. Each of these buildings has to be enhanced, if not, you know, not harmed by the new development. So this is another recommendation I would give you. If whatever you are designing, model also the context. Try to understand the consequences for the context. I will not spend much more words on the regenerative agenda and how this is a landing surface for bird migration, and how this contributes to urbanite island. This can be requires much more time, but perhaps it's interesting the envelope where each facade is creating thermal symmetry. Each let's say change from let's say double facade to trombe wall to different colors create different luminosity and different thermal condition, different surface temperature on the indoor. This means that our body has different thermal stimuli, and all research today support, especially those for diabetics, but also for general health, support that the envelope has to create differential surface temperature. The death of the human is when you want a space which has the same temperature everywhere, which is actually what you do with radiant system and what you want to achieve in any of the passive house or any of the commercial development as this type of agenda, which actually is the fastest track to generate some of the diseases of those working in two offices, especially. So we have to incorporate always the latest finding of sciences. Never believe to what circulate as information into the building field. Skip completely all the information that comes from the building field. Go directly to science, look at thermal comfort literature from medicine, and then try to implement that. This is the latest project I showed. This is with Bjarke and Ingels, where I could curate part of the sustainable strategy. In this case, the idea is to is in the Faroe Island, is an educational center. One big thing is that each building creates local microclimate. Each building also relates to different winds and to different thermal exchanges with the other building inside, and especially with the vegetation. So when you have sites with a lot of wind coming from everywhere, it's very important, for instance, to create external thermal zones where at each time there is always at least one thermal zone which is protected from strong prevailing wind. So when the wind comes from here, we know that this zone is in comfort. When the wind comes from here, we know that the back part is in comfort. So this allows it to 365 days usability of the space. Another concept were related to perhaps daylighting, one aspect that we could simulate in this Mirror Sky lab in that run in Copenhagen. And this has led, for instance, to a design where only the structure is an opaque surface, but each of the other surface is actually in glass, so that light can penetrate even in the basement of the building, providing enough lux to conduct activity, and also establish visual connection between indoor and outdoor. Here is some images of the working space at the basement, where you can see natural light. It's quite abundant. Also, in this concept, the idea is to create different type of facade with different reflectivity on the indoor and the outdoor, as a way to continuously stimulate this relation within the human body, thermal perception. Okay, in summary, not to take more of your time. So the key messages that I wanted to convey are that architecture should connect as much as possible to ecosystem. Perhaps I haven't shown much of nature-based solution. I can do this another time, but I think each object that we build should try to pose the question, what are we giving to the environment with this project? The second is, what are we giving to people with this project? And not only the people that live in the building, but what are we giving to the surrounding in order to create this relation between human and nature? And also, how can we design building that gives more in terms of, for instance, absorbing pollution or create energy to the context? And how facade can provide a climate for the outdoor? And last but not least, health. How can we create, let's say, architecture that promotes health and increase, let's say, our physiological and mental condition throughout all the stage of experiencing the building and the city. Last, and this is the very last slide, here is a book done also in collaboration with some top researchers in Europe and elsewhere, that describe perhaps some of these concepts that were shown here throughout my research, but these are examples from other workers within the field across the world. So you can download that in ResearchGate under Emanuele Naboni. Yeah, so last, feel free to reach me in LinkedIn, Facebook, or through email. So thank you very much for your for being there still after 1 hour.